Back in 2007, I talked with Rob Manning, engineer extraordinaire at the Jet Propulsion Laboratory, and he told me something shocking. Even though he had successfully led the entry, descent, and landing (EDL) teams for 3 Mars rover missions, he said the prospect of landing the human mission on the Red Planet might be impossible. But now, after nearly 20 years of work and research, as well as more successful Mars rover landings, Manning says the outlook has vastly improved. "We've made huge progress since 2007, Manning told me, when we chatted a few weeks ago in 2024. "It's interesting how it's evolved, but the fundamental challenges we had in 2007 haven't gone away, they've just morphed. The problems arise from the combination of Mars' ultra-thin atmosphere, which is over 100 times thinner than Earth's, and the ultra-large size of spacecraft needed for human missions, likely between 20 to 100 metric tons. Many people immediately conclude that landing humans on Mars should be easy," Manning said back in 2007. "Since we've landed successfully on the Moon, and we routinely land human-carrying vehicles from space to Earth, and since Mars falls between the Earth and the Moon in size and in the amount of atmosphere, then the middle ground of Mars should be easy. But Mars' atmosphere provides challenges not found on Earth or the Moon. A large, heavy spacecraft streaking through Mars' thin, volatile atmosphere only has just a few minutes to slow from incoming interplanetary speeds. For example, the Perseverance rover was traveling 12,100 miles per hour, 19,500 kph, when it reached Mars. To under Mach 1, and then quickly transition to a lander to slow, to be able to touch down gently. In 2007, the prevailing notion among EDL engineers was that there's too little atmosphere to land like we do on Earth. But there is actually too much atmosphere on Mars to land heavy vehicles, like we do on the Moon, by using propulsive technology alone. "We call it the supersonic transition problem," said Manning, again in 2007. "Unique to Mars, there is a velocity-altitude gap below Mach 5. The gap is between the delivery capability of large entry systems at Mars and the capability of super and subsonic decelerator technologies to get below the speed of sound. The largest payload to land on Mars so far is the Perseverance rover, which has a mass of about 1 metric ton. Successfully landing Perseverance and its predecessor Curiosity required a complicated, Rube Goldberg-like series of maneuvers and devices, such as the sky crane. Larger, human-rated vehicles will be coming in even faster and heavier, making them incredibly difficult to slow down. "So how do you slow down to subsonic speeds?" Manning said now in 2024, as the chief engineer at JPL. "To get to speeds where traditionally we know how to fire our engines to enable touchdown. We thought bigger parachutes or supersonic decelerators like lofted low Earth orbit flight test of an inflatable decelerator, tested by NASA, would allow us to maybe slow down better, but there were still issues with both those devices. But there was one trick we didn't know anything about," Manning continued. "How about using your propulsion system and firing the engines backwards, retropropulsion, while you are flying at supersonic speeds to shed velocity?" Back in 2007, we didn't know the answer to that. We didn't even think it was possible. Why not? What could go wrong? When you fire engines backwards, as you are moving through an atmosphere, there's a shock front that forms and it would be moving around, Manning explained. So it could come along and whack the vehicle and cause it to go unstable or cause damage. You're also flying right into the plume of the rocket engine exhaust, so there could be extra friction and heating possibilities on the vehicle. All of this is very hard to model, and there was virtually no experience doing it. As in 2007, no one had ever used propulsive technology alone to slow and then land a spacecraft back on Earth. This is mostly because our planet's beautiful, luxuriously thick atmosphere slows a spacecraft down easily, especially with a parachute or creative flying, as the space shuttle did. People did study it a bit, and we came to the conclusion it would be great to try it and find out whether we could fire engines backwards and see what happens." Manning mused, adding that there wasn't any extra funding lying around to launch a rocket, just to watch it come down again to see what happened. Let's pause for a few seconds and give me a like for this video. Thank you so much. But then, SpaceX started doing tests in attempt to land their Falcon 9's first stage booster back on Earth to reuse them. SpaceX said they were going to try it, Manning said. And to do that, they needed to slow the booster down in the supersonic phase while in Earth's upper atmosphere. So there's a portion of the flight where they fire their engines backwards at supersonic speeds through a rarefied atmosphere, which is very much what's like at Mars. As you can imagine, this was incredibly intriguing to EDL engineers thinking about future Mars missions. After a few years of trial, error, and failures, on September 29, 2013, SpaceX performed the first supersonic retropropulsion (SRP) maneuver to decelerate the re-entry of the first stage of their Falcon 9 rocket. While it ultimately hit the ocean and was destroyed, the SRP actually worked to slow down the booster. NASA asked if their EDL engineers could watch and study SpaceX's data, and SpaceX readily agreed. Beginning in 2014, NASA and SpaceX formed a 3-year public-private partnership centered on SRP data analysis called the NASA Propulsive Descent Technology (PDT) project. The F9 boosters were outfitted with special instruments to collect data, specifically on portions of the entry burn, which fell within the range of Mach numbers and dynamic pressures expected at Mars. Additionally, there were visual and infrared imagery campaigns, flight reconstruction, and fluid dynamics analysis, all of which helped both NASA and SpaceX. To everyone's surprise and delight, it worked. On December 21, 2015, an F9 first stage returned and successfully landed on Landing Zone 1 at Cape Canaveral, the first ever orbital-class rocket landing. This was a game-changing demonstration of SRP, which advanced the knowledge and tested the technology of using SRP not only on Earth, but on Mars too. Based on the analyses completed, the remaining SRP challenge is characterized as one of prudent flight systems engineering, dependent on maturation of specific Mars flight systems, not technology advancement, wrote an EDL team detailing the results of the PDT project in a paper. In short, SpaceX's success meant it wouldn't require any fancy new technology or breaking the laws of physics to land large payloads on Mars. "It turns out we learned some new physics," Manning said. They found that the shock front bubble created around the vehicle by firing the engines somehow insulates the spacecraft from any buffeting, as well as from some of the heating. EDL engineers now believe that SRP is the only Mars entry, descent, and landing technology that is intrinsically scalable across a wide range and size of missions, to shed enough velocity during atmospheric flight to enable safe landings. Alongside aerobraking, this is one of the leading means of landing heavy equipment, habitats, and even humans on Mars. But still, numerous issues remain unsolved when it comes to landing a human mission on Mars. Manning mentioned there are multiple unknowns, including how a big ship, such as SpaceX's Starship, would be steered and flown through Mars' atmosphere. Can fins be used hypersonically, or will the plasma thermal environment melt them? The amount of debris kicked up by large engines on a human-sized ship could be fatal, especially for the engines you'd like to reuse for returning to orbit or to Earth. So how do you protect the engines and the ship? Mars can be quite windy, so what happens if you encounter wind shears or a dust storm during landing? What kind of landing legs will work for a large ship on Mars' rocky surface? Then there are logistics problems, such as how will all the infrastructure get established? How will ships be refueled to return home? This is all going to take a lot of time, more time than people realize, Manning said. One of the downsides of going to Mars is that it is hard to do trial and error unless you are very patient. The next time you can try again is 26 months later, because of the timing of the launch windows between our two planets. Holy buckets, what a pain that is going to be. But I think we're going to learn a lot whenever we can try it for the first time. And at least the supersonic retropropulsion question has been answered. We're basically doing what Buck Rogers told us to do back in the 1930s. Fire your engines backwards while you're going really fast. This is the analysis by Nancy Atkinson. She is a space journalist and author with a passion for telling the stories of people involved in space exploration and astronomy. What about you? What are your thoughts on this issue?